Okay, so this is June 2009 and this is the CA paper of the old specification. So question 1 is a titration type question, and if you have a read the question there, 20 centimetres cubed of 0.3 moles per decimeter cubed of potassium hydroxide solution is exactly neutralised by, and then it gives you some options of volumes and concentrations of sulfuric acid. So the first thing we need to do in order to answer this question is to write a balance symbol equation for this reaction. So we've got potassium hydroxide first of all, and if you're not sure you need to do your swap and drop, so I'll do that up here. So potassium hydroxide, potassium is K, it's in group 1, so it has a valency of 1. Hydroxide, its formula is OH, and it has a charge of minus, and so that means that its valency is 1 as well. So we swap and drop that, and so our formula of potassium hydroxide is KOH. So KOH plus sulfuric acid, which is H2SO4, gives us, now we've got a metal hydroxide plus an acid, so that's going to give us a salt plus water. Okay, so just to write that general equation, metal hydroxide plus acid gives us a salt plus water. Now our salt is going to be potassium sulfate, and again we need to do our swap and drop for this. So I'll do that in pink up here. So again, potassium has a valency of 1. Sulfate has a charge of 2 minus, and so that means its valency is 2. I'll just rub out the charge there, we don't need that. And then we swap and drop, and we're going to get K2SO4. It's really important that you do that, otherwise your balance symbol equation will be wrong. So K2SO4 plus H2O. Now we can see that our equation is not balanced. So we've got 2 potassiums on the right hand side, but only 1 on the left, and so we need to put a big 2 here. And then that means we've got 2 waters here, so 2 times our 1 here, that's 2 plus another 2 here. So we've got 4 hydrogens on the left hand side and only 2 on the right hand side, so I've put a big 2 there. And then that's us totally balanced. Okay, if you need to write it out the long way, then do that. Okay, so going back to the question, we have 20 centimetres cubed of 0.3 moles per decimeter cubed potassium hydroxide. Okay, so we're going to use the equation N equals CV. Okay, just to list what we have, we know that the concentration is 0.3 moles per decimeter cubed, and the volume is 20 centimetres cubed, but remember we need to convert that into decimeters cubed, so we divide by 1000, which gives us 0.02 decimeter cubed. Okay, so putting that into the equation, N equals CV equals 0.3 times 0.02, which gives us 6 times 10 to the minus 3, or 0.006 moles. Okay, so the next step in this question is to work out how many moles of sulfuric acid we would need to neutralise this 0.06 moles of potassium hydroxide. And so we bring this over to our sulfuric acid, but we need to remember to take into consideration our stoichiometric ratio. And you can see that the ratio is 2 to 1. So that means that to neutralise 0.6 moles of potassium hydroxide, I need 0.003 moles of sulfuric acid. Okay, so now we need to go back to the options that they gave us in the question. Okay, and we'll do this off to this side. Hopefully you can still see that. So remember, we need 0.03 moles of sulfuric acid. That's our aim. So we need to go through each of these options and see which gives us 0.03 moles. So the first option, option A, is 10 centimetres cubed of 0.3 moles per decimetre cubed. So we use our equation N equals CV. Our concentration is 0.3 moles per decimetre cubed, and our volume is 10 centimetres cubed, but we need to divide that by 1,000, and that equals 0.01 decimetre cubed. So putting that into our equation, N equals CV, it's equal to 0.3 times by 0.01, and putting that into our calculator, we get 0.003 moles, which is exactly what we're looking for. So our answer is A. Question number 2 is an electronic configuration question. So we can see we've got the important parts here are we've got a positively charged particle, and then we've got its electronic configuration. And so the best way to do this is just to total up the number of electrons you have in this configuration. So we've got 1s2, 2s2 electrons, and 6 2p electrons. So that gives us a total of 10 electrons. And then it's working out for each of these ions how many electrons they have. So we're looking for the ion that has 10 electrons, but also the ion that has a positive charge. So let's look at aluminium first of all. So you need to, at this stage, look at your periodic table and find aluminium. So aluminium is in the periodic table. It looks like this. Aluminium, its mass number is 27, its atomic number is 13. Okay, so we look at this lower number. It has 13 electrons. So if we'll just do aluminium in a bit more detail. We'll not do this with all the others. Aluminium has 13 electrons. So in the first shell we've got 2. Second shell we have 8. And then in the third shell, that's us up to 10 electrons now. The third shell we have 1, 2, 3 electrons. Now remember that ions form from atoms when atoms lose or gain electrons in order to get a full outer shell. So what aluminium is going to do, because it's in group 3 and it's a metal, it's going to lose electrons. So we are going to get rid of this electron, and this electron in order to get a full outer shell. So I'll just take that away now. So we did have 13 electrons, but we've taken out the outer 3 electrons. And so now you can count up the electrons in the picture, or we can think about it as a calculation. We had 13 electrons, we took away 3, and now we have 10 electrons. So we can see that we've got the correct number of electrons for our answer, but do we have the correct charge? Well, what happens when an atom loses electrons? Think about each electron carrying a negative charge, and so our aluminium ion, because it's lost 3 electrons, has a charge of 3+. So here we've got our answer because we've got an ion that has 10 electrons. So it's going to have the same configuration as 1s2, 2s2, 2p6 as in the question. But also it's got a positive charge. So our answer is A. Just to look at what it would look like with fluorine. Fluorine, if you look on the periodic table, it appears like this, which means that it has 9 electrons in the atom. So fluorine is 9 electrons. But what happens with fluorine when it forms an ion, the fluoride ion? Well, it gains an electron. And so it has a total of 10 electrons, which gives us the number of electrons that we are looking for. But think about the charge on the fluoride ion. Fluorine has gained an electron, and so it has a charge of minus. So therefore it can't be our answer. And it will be the same with oxide. Oxygen has 8 electrons. It will then gain 2. So its ion will have 10 electrons, but its charge is 2 minus. And then with potassium, it has 19 electrons, loses 1, and so its ion will have 18 electrons, and so it's not correct either. So our answer for number 2 is A. Question number 3 is looking for a molecule that has a triple bond. So the best way to do this is draw out the structure of your 4 molecules to make sure you've got the right one. So first of all, A. A is a molecule of ethene, which we know has a double bond between the 2 carbons and the 4 hydrogens coming off like this in single bonds. And so we've got 1 double bond and 4 single bonds, but no triple bonds. Molecule B is carbon dioxide. So we've got a carbon in the centre, which is double bonded to an oxygen, and it's double bonded to another oxygen to give us CO2. So again, we've got 2 double bonds, but no triple bonds. Molecule C is nitrogen N2. So we've got 2 atoms of nitrogen, and we need to think about how they are bonded. Well, nitrogen likes to form 3 bonds, so its molecule, its diatomic molecule, exists as 2 nitrogen atoms that have a triple bond between them. So here we've got nitrogen has a triple bond, and so our answer is C. And just to check, molecule D is nitrogen trifluoride. So we've got nitrogen singly bonded to 3 fluorine atoms. Because fluorine can only form 1 bond, nitrogen likes to have 3 bonds. So there's only 3 single bonds in molecule D. Question number 4 asks about which of the sodium compounds produces a gas when treated with dilute sulfuric acid. Now, before you panic and think this is to do with the halogens topic, it's not. Think about what you're being asked here. Each of these, if they were treated with dilute sulfuric acid, which would produce a gas? Well, let's look at sodium carbonate. What is sodium carbonate? Well, it's a metal carbonate. When we react a metal carbonate with acid, what do we get? We're back to our general equations here. Salt plus water plus carbon dioxide, which is obviously a gas. And so your answer is A. Sodium carbonate will react with dilute sulfuric acid to give us a salt, which will be sodium sulfate, because we're using a sodium compound and sulfuric acid. We'll get water and we'll get carbon dioxide gas being given off, which obviously is a gas, and so your answer is A. Question number 5 is another titration question, but this type of titration has been moved to module 5, which we will look at next year. So you don't have to do that, but just if you want to complete it, the answer is C. We use sodium thiosulfate and starch when we do an iodine titration. Question number 6 is about electron arrangements in the subshells. And the question asks, which one of the following has 2 unpaired electrons in its electronic configuration? And so the best way to do this is to draw out all the arrangements of the electrons in the shell. So we'll talk about, after we do that, maybe a shorter way of doing it, but for completeness sake we will do them all out. So first of all, we've got A, which is 1s2, 2s2. And so we've got 1s and 2s. There's 2 electrons in 1s and 2 electrons in the 2s. So you can see there's no unpaired electrons. Then for B, we've got 1s2, 2s2 and 2p3. So we need to do our 1s2, our 2s and our 2p, which has 3p orbitals. So we've got 2 in 1s, 2 in 2s, and then we've got 1, 2, 3. And remember, electrons only pair up when they have to. So those 3 electrons stay unpaired before they start pairing up. And so you can see that in B we've got 3 unpaired electrons, so we don't have the right answer yet. Then for C, I'll draw C in the middle here. So C, we've got 1s, we've got 2s, and we've got our 2p, and there's 3 of those. Okay, so we've got 1s2, 2s2, and then 2p4. Again, the electrons remain unpaired when they can, but I've got 4 electrons in the 2p subshell. So I need to put my 4th one in here, paired up with that the 2px orbital, so to speak. So we can see that we've got 2 unpaired electrons here. We've got 1, 2 that are unpaired, and so our answer is C. But just to draw D out to give you an idea of what that looks like, I'll draw it up here. So D is, we've got 1s, we've got 2s, we've got 2p, so there's 3 orbitals in that. We've got the 3s orbital and then the 3p again with 3 orbitals. So 1s2, 2s2, 2p6, so 1, 2, 3, 4, 5, 6, 3s2, and then 3p5. So the electrons would fill in this order, 1, 2, 3, and then they have to pair up 4, 5. And you can see that you've just got 1 unpaired electron, so it's not D either. Now, a slightly quicker way to do this is just to take the final subshell in each of the cases, because if you think about it, the final subshell is going to be the only one that can have unpaired electrons. All the others, now apart from transition metals, there's a couple of exceptions in that case, but for most other electronic configurations, you can see that the lower subshells are always complete. So take D, the example we've just done. This subshell is full, this subshell is full, this subshell, this, all of these orbitals in that subshell. This subshell is full. It's only when we get to our last subshell, that we could possibly have unpaired electrons, because they're the only ones that couldn't be complete, because we know that electrons always fill the lower energy subshells first. Now, as I said, there's some exceptions in the case of transition metals, but that's when we get into our 4s and our 3d electrons. So in this case, we could have just drawn the last of the subshells in each case. So 2s, 2p, 2p, and 3p. Okay, and that would have saved us a little bit of time, but it is important that you draw it out just to make sure. And also that you remember that in the case of 2s, there is 1 orbital. In the case of 2p, there's 3 of those orbitals. Question 7 relates the electronic configuration of an element with its location on the periodic table, and it asks which area contains elements which only have s electrons in their outer shell. And this is something you should know, that this section of the periodic table, in fact this whole section here, this is called the S block, this is called the D block, and this is called the P block. So anything in the S block has its outer shell configuration ending in S electrons. This middle block or transition block has its electronic configuration ending in D electrons, and this section, the green section, has its outer shell configuration ending with P electrons. And so our answer is then going to be A. So your answer for 7 is A. Now if you think about it, let's take an example from that block. Lithium sits in that block. Lithium has 3 electrons, and so its outer shell configuration is 1s2, 2s1. Then another example would be magnesium. Magnesium has 12 electrons, and so it's 1s2, 2s2, 2p6, 3s2. Again, you can see the outer shell configuration is always got s electrons. Question 8 asks you to identify the non-polar compound out of these options. And so what we need to do here is we need to draw our molecules out and draw their dipoles. So remember that within a molecule we can have dipoles, we can have polar bonds within the molecule, but they can still be overall non-polar if those dipoles cancel each other out. So let's start by drawing out our molecules. Firstly, we've got HCl. So if we draw our hydrogen chloride, and it's important in this case that we know the shape of our molecules. And so obviously hydrogen chloride is just linear. Which is going to be your more delta negative, that's going to be your chlorine. And the hydrogen is going to be delta positive. So we can draw our dipole like this. Okay, so we've got a dipole within this. There's only one dipole and it's in one direction. And so compound A is going to be polar. Let's have a look now at compound B. And we've got a carbon with 4 chlorines. So just like methane, this is going to be tetrahedral. Got 4 bonding pairs, so it needs to be tetrahedral. So we've got CCl here, CCl here, CCl bond here. That would stick out in the plane of the page. And one that's going back. Okay, so thinking about our polarity here again, the delta negative is going to be on the chlorine, the delta positive on the carbon, and that will be the same for each of our bonds. And so we can draw our dipoles in this direction for each of the CCl bonds. Now, we have dipoles within this molecule, so there's polar bonds within this molecule, but the dipoles are going to be equal because they have the same electronegativity difference between carbon and chlorine. So because they're the same bond, the dipoles are going to be of the same strength, but the dipoles are all in opposite directions. And so what we find is that the dipoles actually cancel each other out. So the dipoles cancel. We've got complete symmetry in this molecule. And so this is overall non-polar. Yes, there's dipoles within the molecule, but they cancel each other out. So this is our non-polar molecule. So our answer is B. Let's just have a look at C and D to have a look at their shape. C is carbon in the centre, 3 hydrogens and 1 chlorine. So we'll draw the chlorine up here, and then our 3 hydrogens. Now, in organic chemistry, we tend to just ignore the dipole on the carbon-hydrogen bond. Yes, there's a small electronegativity difference, but it's not significant enough for us to consider. And so we'll just draw our dipole from our delta positive carbon to our delta negative chlorine. And so, yes, we've got symmetry within this molecule, but we have a stronger dipole going from the carbon to the chlorine. And so the overall dipoles do not cancel each other out. So this is overall polar. And then we're going to see the same for D. D, this time I've got 1 hydrogen and 3 chlorines. Okay, so I'm going to see my dipoles coming out this way, and this way. But again, I don't show a dipole between carbon and hydrogen. So yes, this molecule has symmetry, but not in terms of its dipoles. There will be an overall dipole that will go down the way in this molecule. So this is also polar. So we can confirm that our answer is B. Question 9 asks us to identify the molecule which contains a coordinate bond. So you need to think to yourself, what do we need to form a coordinate bond? We need a lone pair of electrons on one molecule that is able to donate, and then we need an empty orbital on the other molecule that is able to accept the lone pair. And so we know that when nitrogen forms compounds, it forms 3 bonds, and that leaves it with 1 lone pair. So take the example of ammonia, and I'm going to draw ammonia on its side here. So we've got a bonding pair here. We would normally draw it sort of rotated 90 degrees. We've got a bonding pair here. And a bonding pair here. And then nitrogen has still a lone pair of electrons, and that's why we see this pyramidal shape of ammonia. So that ammonia molecule has a lone pair of electrons that is able to donate to an empty orbital. So that can donate to an empty orbital, and we use the arrow to show that, the movement of electrons, of how it's donating. And we know that hydrogen plus, a hydrogen ion, has an empty orbital. So if you think about hydrogen and its electronic configuration, it has 1 electron, but when we remove that electron, it has no electrons and it has a positive charge. That means what once was the 1s1 has now become 1s0. So that 1s0 is now an empty orbital that's able to accept the lone pair of electrons from nitrogen. And so we can see that our answer is D. D is the ammonium ion, which is formed when the lone pair on ammonia coordinate bonds with a hydrogen ion. The last question in the multiple choice section asks about one of our definitions of an enthalpy change, which again, this is now on module 2. But hopefully you should remember it. So it asks about the enthalpy of neutralization. Think about a neutralization reaction. We've got an acid reacting with an alkali to give us salt plus water. But you do also need to be familiar with your definition for the enthalpy of neutralization. And that is the energy change involved in a neutralization reaction on the formation of 1 mole of water. Okay, so our answer is B.